How can we determine if a binary number is divisible by some other number? How do I look at these ones and zeros and know if it's divisible by 2 or 3 or 4 or anything at all? Well, today we're going to go over the divisibility rules for binary numbers, and we're going to talk about divisibility rules for 0, 1, 2, 3, and so on up through 10. Super quick review, in case you don't know how binary works, our decimal system is base 10, which means the way we express numbers is based on powers of 10. This first digit represents 2 copies of 10 to the power of 0. Anything to the power of 0 is 1, so that's just representing 2 units. This next digit of 2 represents 2 copies of 10 to the power of 1, so that's 20. This next digit represents 5 copies of 10 to the power of 2. 10 to the power of 2 is 100, so that's 500. And this last digit represents 4 copies of 10 to the power of 3, so that's 4,000. Binary is the same thing, except instead of using powers of 10, it uses powers of 2. And instead of calling them digits, we typically refer to them as bits. So the first bit in this binary number is 1 copy of 2 to the power of 0. 2 to the power of 0 is 1, so that's just 1 unit. This next bit is 0 copies of 2 to the power of 1, so 0 copies of 2. The next bit is 1 copy of 2 to the power of 2, so 1 copy of 4. The next bit is 1 copy of 2 to the power of 3, so 1 copy of 8. And as you can see, the bits of a binary number can only be 0 or 1, because, for example, if I had 2 copies of 2 to the power of 2, well, that's actually just 2 to the power of 3, so I would actually put a 1 in the 2 to the power of 3 bit. Alright, first up, how do we tell if a binary number is divisible by 0? Simple, it isn't. The only number divisible by 0 is 0 itself, otherwise not divisible by 0. Alright, next up, how do we tell if a binary number is divisible by 1? Simple, it is. Every number is divisible by 1. Alright, now it's getting harder. How do we tell if a binary number is divisible by 2? Well, in binary, 2 functions a lot like 10 does in the decimal system, as we went over. In our decimal system, we know that a number is a multiple of 10 if it ends in a 0. Same thing in binary. For a number to be divisible by 2, it needs to end in a 0. For example, this binary number is not divisible by 2 because it has this 1 unit at the end. That means it's certainly an odd number and not divisible by 2. On the other hand, this binary number has a 0 at the end. That's the very first bit, so this means it's definitely even. Remember, all of these other bits are representing non-zero powers of 2, so all of those represent things that are definitely even. The only way a binary number could fail to be even is if it had a unit at the end, and this does not, so it's divisible by 2. Any binary number that ends in a 0 is divisible by 2. Now, how do we know if a binary number is divisible by 3? This one's actually kind of tricky, and it's basically the same as the 11 divisibility rule in the decimal system. 11 is 1 more than 10, 3 is 1 more than 2, so that's why they're similar. For the divisibility rule for 3 to make sense, we just need to look back at how the binary system works. Remember, the smallest bit is representing units. A unit is 1. And 1 is 1 more than a multiple of 3, because 0 is technically a multiple of 3. The next bit up would be 2 to the 1. 2 to the 1 is 2, and 2 is 1 less than a multiple of 3. Then we have 2 to the 2, which is 4, which is 1 more than a multiple of 3. Then we have 2 cubed, which is 8, which is 1 less than a multiple of 3, and so on. The powers of 2 alternate between being 1 more and 1 less than multiples of 3. So, to determine if a binary number is divisible by 3, all we actually have to do is calculate the alternating sum of the bits. For example, look at this binary number. To see if it's divisible by 3, we take the first bit, subtract the second bit, add the third bit, subtract the fourth bit, add the fifth bit, subtract the sixth bit. It's just the alternating sum of the bits. We see that this is 1 minus 1 is 0, minus 1 is negative 1, plus 1 is 0, minus 0 is 0. This is equal to 0, and if you get 0 when you do this, then yes, it's a multiple of 3. This binary number happens to equal 54 in decimal, and clearly 54 is a multiple of 3. On the other hand, if we take this binary number, 11111, if we calculate the alternating sum, this is 1 minus 1 plus 1 minus 1 plus 1, and that is, let's see, 0, 0, 1. This is equal to 1. That's not 0, so this is not a multiple of 3. In fact, this binary number happens to be 31 in decimal form, clearly not a multiple of 3. Now, what about 4? Well, remember, we're working in a base 2 system. Because of that, the divisibility rule for 2 was very similar to our familiar decimal rule for divisibility by 10. In the same way, 4 is of course equal to 2 squared. So the divisibility rule for 4 is just like the decimal divisibility rule for 10 squared, which is 100. To know if a number is divisible by 100 in decimal, we just check if the last 2 digits are 0. Same thing in binary with divisibility by 4. For example, look at this binary number. The last 2 bits here are 0, so we know it's divisible by 4, because every bit after those first 2 is itself counting multiples of 4. Like, this is counting 2 squared. 2 squared is a multiple of 4. This is counting 2 cubed, which is 8, which is a multiple of 4. This is counting 2 to the 5, which is 32, which is a multiple of 4. The only place we could have something that's not a multiple of 4 is in these first 2 bits, where this one is representing units, and this one is representing copies of 2. But as long as those are both 0, guaranteed, this is going to be a multiple of 4. On the other hand, a number like this would not be a multiple of 4, because its last 2 bits, or first 2, depending on your perspective, they are not 0, 0. This is another binary number that would not be a multiple of 4, because those 2 bits at the end are not 0. Next, how do we know if a binary number is divisible by 5? This one's a little bit tricky. Remember the divisibility rule for 3. Because 3 is 1 more than our base, which is 2, we were able to determine divisibility by 3 by calculating the alternating sum of the bits. So for 5, what we're going to do is convert our binary number to base 4, which is easy because 4 is a power of 2, and 5 is 1 more than 4. So then again, we can just use the alternating digit trick. I use the word digit just because we don't have a specific name for the digits in base 4. Now, like I said, converting a binary number to base 4 is easy. Let's just make sure you know what the first 4 numbers look like in binary. So 0, 0, that of course is equal to 0. On the other hand, 0, 1 is equal to 1, and then 1, 0 is equal to 2, and then 1, 1 is equal to 3. So to convert a binary number to base 4, all we have to do is look at pairs of digits, and whatever they're equal to, 0, 1, 2, or 3, that will be the digit in base 4. Like I said, we have to look at pairs of digits, but if our binary number does not have an even length, we just imagine that we've put a 0 at the beginning to fix that. So for example, here is a binary number, and I want to know if it is divisible by 5. To that end, I'm first going to rewrite it in base 4. So look at this first pair of digits, 1, 0, that is 2, so that's the first digit in base 4. Then 1, 1, I know that's 3, so that's the second digit in base 4. And then 0, 1, that's just 1, and so that is our last digit in base 4. So this is in base 4, and so we can just use the alternating sum of the digit trick to check if it's divisible by 5. That's because just like with the powers of 2, the powers of 4 alternate in how they relate to multiples of 5. 4 to the power of 0 is 1, which is 1 more than a multiple of 5 because 0 is technically a multiple of 5. 4 to the 1 is 4, which is 1 less than a multiple of 5. 4 to the 2 is 16, which is 1 more than a multiple of 5, and so on. So the alternating sum of these digits in base 4 is 2 minus 3 plus 1, and this is equal to 0. So indeed, this is divisible by 5. It happens to equal 45 in decimal. Here's one more example. Here's our binary number, 10111. Let's rewrite it in base 4 so we can check if it's divisible by 5. Notice that this binary number does not have an even length, so when we convert it to base 4, we would imagine that we have a 0 at the front. Then I look at those pairs of bits, 0 and 1, that gives me 1 as the first digit in base 4. 0 and 1, that gives me 1 as the second digit. 1 and 1, remember that gives us 3 for the last digit in base 4. So this is base 4, then I calculate the alternating sum of the digits, 1 minus 1 plus 3. This, of course, is not equal to 0, and so this number in binary is not divisible by 5. It happens to be equal to 23 base 10. Next up, divisibility by 6. Oh, that is easy because 6 is equal to 3 times 2. So to be divisible by 6, a number just has to be divisible by 3 and divisible by 2. And we've already discussed divisibility rules for both of those. So if I have a binary number, I need to check if it ends in 0. If it is, it's divisible by 2. And then I can calculate the alternating sum of the bits. If it's 0, then the number is divisible by 3. And thus, if it's divisible by both 2 and 3, it would be divisible by 6. Next up, 7 and skip. We're going to come back to that one. Next up, 8. 8 is really easy because it's a power of 2, just like 2 and 4. We just need to check that the last 3 bits end in 0 for a binary number to be divisible by 8. For example, this one is certainly divisible by 8, whereas this one is not divisible by 8. Just check the last 3 bits. If they're 0, then the number is divisible by 8. Next up, 9. For 9, we're going to use the same sort of trick that we used for divisibility by 5. Instead of converting our binary numbers to base 4, though, we'll convert them to base 8. 9 is one more than a base of 8, so then we'll be able to use the alternating sum of the digits trick. When converting binary numbers to base 4, we had to look at pairs of bits at a time, because pairs of bits can cover all numbers from 0 to 3, which are all available digits in base 4. In base 8, the available digits are 0 through 7, and so we'll actually need to look at 3 bits at a time. Just as a couple of quick examples, 101, this is 1 copy of 2 to the power of 0, plus 0 copies of 2 to the power of 1, plus 1 copy of 2 to the power of 2. So it looks like this. Thus, of course, this binary number is equal to 5. And so that's what it would look like in base 10 as well as base 8, but we'll need to do that for all triples of bits for a binary number. So for example, here's a binary number, 11011. I want to look at 3 bits at a time. You can see there are 3 bits there, and we just imagine there's a 0 at the front to give us another 3 there. These 3 bits represent 1 unit plus 1 copy of 2, so that's 3. And this is the same thing. So this is a 2-digit number. In base 8, it's 3. Then, to check if it's divisible by 9, I would calculate the alternating sum of the digits. Of course, that's 3 minus 3, which is 0. If we get 0, then yes, the original binary number is divisible by 9. This one turns out to equal 27 in base 10. Here's a longer example, 11111111010. Again, I want to look at 3 bits at a time, so I want to make sure I identify those triplets. We imagine 2 zeros at the front to give us that one more triplet, and then convert these triples into our digits base 8. This represents 1, this represents 7, this represents 7, and this represents 2. So that's what the number looks like in base 8. Then we calculate the alternating sum of the digits. It's 1 minus 7 plus 7 minus 2. And this is not equal to 0, so the original binary number is not in fact divisible by 9. This number happens to equal 1018 base 10. Now, divisibility by 10 in base 2 works just like divisibility by 6, which is to say we just have to look at the factors. So 10 can be factored into 2 times 5, so all we have to do to know if a binary number is divisible by 10 is check if it's divisible by both 2 and 5. To check if it's divisible by 2, we check if the bit at the end is 0, and to check if it's divisible by 5, we do the conversion into base 4 and then calculate the alternating sum of the digits. Alright, I guess guess we need to finish with divisibility by 7. This isn't too complicated, but you gotta work with me for a minute here. Let me just write a fairly lengthy binary number over here on the left. Remember, all of these bits are counting powers of 2. This is one copy of 2 to the 0, 0 copies of 2 to the 1, 0 copies of 2 to the 2, 1 copy of 2 to the 3, and so on. I'm going to write those powers of 2 in a certain way that will be illuminating for us for divisibility by 7. 2 to the power of 0 is the same as 2 to the power of 3 times 0. And then 2 to the power of 1 is 2 to the power of 3 times 0 plus 1. And then 2 to the power of 2, well, that's the same as 2 to the power of 3 times 0 plus 2. 2 to the power of 3, I'll write it up here so I have more room, that's the same as 2 to the power of 3 times 1. 2 to the power of 4, well, that's the same as 2 to the power of 3 times 1 plus 1, and so on. Note how we're expressing each exponent in relation to multiples of 3. So this is a multiple of 3. This is 1 more than a multiple of 3. This is 2 more than a multiple of 3, and so on. This next exponent is a multiple of 3, then 1 more than a multiple of 3. The next one would be 2 more than a multiple of 3, and then we'd get another multiple of 3. Now, we need to make some remarks about numbers of these forms. Numbers of the form 2 to the power of 3 times a thing, and 2 to the power of 1 more than a multiple of 3, and 2 to the power of 2 more than a multiple of 3. All of these numbers, these multiple 3 powers of 2, these are numbers like 1, 8, 64, and so on. We say that all of those numbers are congruent to 1 mod 7. This means if we divided these numbers by 7, we'd have a remainder of 1. For example, 8, if you divide it by 7, you get 1 with the remainder of 1. 64, if you divide by 7, you get 9 with the remainder of 1. On the other hand, these numbers, powers of 2, where the exponent is 1 more than a multiple of 3, these are all congruent to 2 mod 7. So when numbers of this form are divided by 7, you get a remainder of 2. For example, 2 to the power of 4 is 16. 16 divided by 7 is 2, with the remainder of 2. Finally, numbers like this, powers of 2 where the power is 2 more than a multiple of 3, these are all congruent to 4 mod 7. When a number of this form is divided by 7, there is a remainder of 4. These are numbers like 2 to the power of 5, which is 32, divided by 7 is 4, with the remainder of 4. Now, remember how we were able to check if a binary number is divisible by 3 by calculating the alternating sum of the bits? That worked because the powers of 2, which make up the binary system, alternate between being 1 more than a multiple of 3 and 1 less. 1 more, 1 less, and so on. The same thing's happening here with 7, but it's a little bit more complicated. The powers of 2, which make up the binary system, alternate between being 1 more, 2 more, or 4 more than a multiple of 7. 1, 2, 4, 1, 2, 4, and so on. So for divisibility by 7, instead of taking the alternating sum of the bits, we need to carefully take a bit, multiply it by 1, go to the next bit, multiply it by 2, go to the next bit, multiply it by 4, go to the next bit, multiply it by 1, and so on until we've done it for all bits, add it together, and if we get a multiple of 7, then the number is divisible by 7. And we have to make sure we do the multiplication right, so when this process is applied, you should go from right to left in the binary number, starting with 2 to the 0, then 2 to the 1, then 2 to the 2, then 2 to the 3, then 2 to the 4, then 2 to the 5, and so on. All right, we are ready for an example. Here's my binary number, 1, 1, 0, 0, 0, 1. Remember what we're going to do. We're going to go from right to left and multiply the bits by 1, then 2, then 4, then 1, then 2, then 4, and so on. Add them together, see if we get a multiple of 7. First bit, I multiply it by 1, I get 1. Then multiply by 2, that's 0. Multiply by 4, that's 0. Multiply by 1, that's 0. Multiply by 2, that's 2. Multiply by 4, that's 4. 1 plus 2 plus 4, that's 7, which is a multiple of 7, so indeed this binary number is divisible by 7. It happens to equal 49 in base 10. Here is another example, 1, 1, 1, 1, 1, 1. To check for divisibility by 7, the first bit we multiply by 1, the next bit we multiply by 2, the next bit we multiply by 4, the next bit we multiply by 1, the next bit we multiply by 2, the next bit we multiply by 4. This is 1 plus 2 plus 4 plus 1 plus 2 plus 4. That's 14, which is a multiple of 7. So this number is divisible by 7. It happens to equal 63 base 10. On the other hand, one more example, 1 0 0 0 0 1 0. Here's another binary number. Let's check divisibility by 7. First bit we multiply by 1, that's 0. The next bit we multiply by 2, that's 2. Next bit we multiply by 4, that's 0. Next bit multiply by 1, it's 0. Multiply by 2, 0. Multiply by 4, 0. Multiply by 1, that's 1. So 2 plus 1, which is 3, which is not a multiple of 7. So this binary number is not divisible by 7. It just happens to equal 66 in base 10. So those are all of the binary divisibility rules for numbers 0 through 10. Hopefully you can see some of the patterns and analogous methods that are similar to the base 10 divisibility rules, and you could come up with your own divisibility rules for other bases. Let me know in the comments if you have any questions, and be sure to subscribe for more of the swankiest math videos on the internet.
From my fate, twisting to escape this. Cutting out my wrist if you can break it. Breaking in my past, I'm making it up fast. So slow down, give me the time so I can fake it. Embrace the tone of words and just how I say shit. And let me speak my poetry to your face. It's not infinite if you ain't listening. Not infinite if you ain't really into it.